which class? Lab or class?
Lab.
That's number. All right, good morning and welcome back to microprocessor course. So in today's class, we are going to have a review class which can help you to get ready for your exam and have a big picture about the exam question types. What do you expect to have in your exam? And we may also have a short in-class quiz on error detection and the correction code, Hamming code in today's class. Before we start today's lecture, I'm gonna check on your attendance. Class 5, number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. '15, '17, '18, '19, '20, '21, '22, '23, '23, '24, '25, '26, '27, '28, '29, '30. Class 6, number 1, number 2, 3, 5, 6, 7, 8, 10, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 21. Class 6, number 21. 22, 23, 24, 26, 26, 27, 28, 29, 30, B21, class 6, 15. Okay, good. Here we go. So in today's class, we're going to have a short review In your exam, you may expect to have multiple choices questions. You may have multiple choices questions. And to solve this kind of problems, you need also to do some calculations. For example, I may give you a type of multiple choices question which you need to apply Amada's law, all CPU time, all million instruction per second. So here you may expect to do also some calculation to find the right answer for these multiple choices question. Second type of questions is more related to drawings, diagrams. So as you have seen in this course, we have many drawings, computer-related drawings. So you better take some time to look at the different drawings that we have in this class and make sure you do understand them. I may ask you to draw something like what you have done in homework number 1. It was about Harvard architecture or von Neumann architecture or the general component of the computer or the instruction cycle state diagram. So you need to pay attention to those kind of diagrams. So the next types of questions is problem to solve. You may need to solve problems related to computer performance metrics. Memory system. So you may also expect to have this kind of problem that we need to solve in this exam. You're going to have different types of questions. Make sure you do pay attention to these details that we're going to see in today's class. So if you still remember, we learned about what is in a computer. We learned about the different components of computer. We have the CPU, we have the main memory, we have the bus system, and input-output devices. We have the CPU, which include as well registers, arithmetic, logic unit. We have control unit, and we have also internal bus to link all those computer systems. Then we have different components of the CU. We have the sequencing logic. We have control unit and the registers. We have also control memory. So this is a big picture of what we have in the computer. So when it comes to computer architecture, we need to understand how components are organized. How components are organized in the computer. We need to learn about the functions, what are the different functions of the computer, how the components operate, and their implementation, hardware realization. We talked about von Neumann architecture, which stores data and instructions in the same memory unit As you can see from this picture that we have on the screen, we have a single memory unit to store data and instructions. So it has the central processing unit, which include the control unit and arithmetic logic unit, and the main characteristic for this von Neumann architecture is that it stores data and instruction in the same memory unit. You have got this in your homework number 1. I ask you to draw this von Neumann architecture and briefly describe this architecture. Now, because of this memory unit which store both data and instruction, the central processing unit cannot get access to data and instruction at the same time. So there is a problem that we call bottleneck problem. So to solve this issue, Harvard architecture was introduced. As you can see from this diagram on the screen, we have a memory unit for data and a memory unit for the memory, for the instructions. That means that the CPU can get access at data and instruction at the same time because we have two different bus systems to get access to data and instruction. So von Neumann architecture, one of its drawbacks is that it stores data and instruction in the same memory unit. Then to solve this issue, Harvard architecture was introduced to allow two different memory units to store data and instruction separately. Moore is law. Moore is law says that the number of transistors on a chip would double every 18 to 24 months. So we have tried to apply this law to help you understand about this. And we talked about Moore's law in CPU world, Moore's law in GPU world as well. Make sure also you do revise Moore's law and its application. We learned about processor technology, shrinking of transistors. We have seen that nowadays we have very, very small computer devices because of shrinking of transistors size to solve different issues related to computer component size as well as heating problem which was there in the beginning of computer systems. So we have seen that there is a shrinking in transistor size. We learned about switched capacitance, power loss. We have activity times capacitance times voltage to the power of 2 times the frequency. Also make sure you do still remember how to apply this switched capacitance power loss and how can we minimize this loss. To improve the computer system performance, there was idea to have many cores on a single processor chip, which can allow the computer to perform very well when it comes to tasks that can be executed in parallel. So we have this multi-core mania to include many cores on a single processor chip. If you still remember, we discussed about this why multi-core mania. We have one core which we need to add one more core to make a dual core. So we have seen that the size of the core needs to be the same. Those need to minimize to have small cores in the same area. So we have seen that the performance of each core does decrease in the dual and the quad multi-core, whereas the performance of the whole chip increases. Why the performance of each core decreases is because there is overhead communication or resource sharing. They need to share the same resources. So for this technique, understand that the performance of each core in dual and the quads is decreasing in as depicted by this table, whereas the performance of the chip is increasing because they come together to perform the same task. But since each core needs to have a greater communication with the other, there might be some overhead communication or resource sharing. That's why here we have the performance P, but here in dual core we have the decrease in performance for each core, and in the quad also we have a decrease in performance because there is overhead communication, and not all tasks can be performed in parallel. Generation of computers, we talked about this the generation of computers. We have seen that vast generation, which was introduced between the 1940s and the 1950s, was characterized by vacuum tubes. That's why we have big computer, and there was high heat generation. We have the second generation of computers, which was introduced between the 1950s and the 1960s. The main characteristics for the second generation of computer was the introduction of transistors. Then third generation of computer, introduction of IC. We have IC that was happened between 1960s and 1970s. Fourth generation, microprocessor, introduction of microprocessors. We learned about evolution of microprocessors, especially for Intel processors. We learned 4-bit processors, 8-bit microprocessors, up to 64-bit microprocessors, and we learned about ARM processors. We learned about different processors. Make sure you understand what is a 4-bit microprocessor, a 16-bit microprocessor, and do have to devise this lecture which can help you where we came from about the evolution of microprocessor, so that you do understand the actual technology when it comes to microprocessors. We have structure of Institute for Advanced Studies. This was designed at the Institute for Advanced Studies in the United States in 1940s. We see that we have the arithmetic logic unit. We have also the PC program counter to hold the address of the next instruction to be executed. We have the memory address register to hold the addresses, memory addresses, and we have instruction register to hold the first instruction. We have also the memory. We have the memory there. We have different memory addresses there. So this is very important to remind you about the different control registers, that we have learned when we talked about 8086 microprocessor. You see, we have these control status registers. Now we have instruction and data. If you see instruction and data stored in the same memory location, in the same memory unit, it helps you to find out that this is based on which architecture, Harvard architecture or von Neumann architecture. We have data and instructions that comes from the same bus system. That means we have data and instructions in this memory system. These are the memory addresses, and we have data and instruction that comes from the same memory addresses. That means the same bus. We have a single bus system to transit data and instruction. That means that this is based on von Neumann architecture. We have a single bus to transit data and instruction. Now we have parallel architectures. If you still remember, we learned about this. Single instruction, single data. That means we have one instruction which need a single data to complete its task. We need one-to-one, that is instruction. one-to-one data. We have one instruction which requires a single data stream to complete its task. For the second one, we have single instruction, multiple data. That means we have a single instruction, which needs many data streams to complete its task. Let's say here for single instruction, single data, you are working on your word processing. You are processing a document in Word, or you are doing calculation. That is a single instruction, single data. Now, for single instruction, multiple data, you have one instruction which requires you to have multiple data streams to complete its task. Now, this is the case of image processing, for example. This is the case of image processing where one instruction needs to be applied on the multiple pixels of the image to understand what it does mean, what the image is. We have here multiple instruction, single data. That means we have many instructions that only need a single data stream. This is more applied in research. Now we have multiple instruction, multiple data. That means we have many instructions that require many data streams to complete their task. So this is parallel architecture is something that we're gonna also continue with advanced microprocessor to understand more about this parallel architecture. Now we're gonna learn about the computer performance metrics. The simple one is million instructions per second. If you still remember, this is the basic measure for CPU performance. It represents how many instructions a processor can execute per second. We have million instructions per second, which million instructions per second equals to instruction counter divided by execution time times 10 to the power of 6. When using the CPU parameters, you can also have million instructions per second equals to the clock length that needs to be in hertz divided by cycle per instruction times 10 to the power of 6. We have a simple example here. We have a measurement for computer A and a measurement for computer B. We want to calculate which computer has higher million instruction rate. We have computer A is instruction counter, that is 10 million. Computer B is instruction counter is 8 million, and we have the CPU time, that is 2 to the power of 5, and we have second, we have the CPU time for computer B, that is 2.2 seconds. Now we can calculate easily the million instruction per second for the computer A, million instruction for the computer B. We have instruction counter 10 million for computer A. We have 8 billion for computer B. Then we have the execution time for the computer A, 2.5 seconds. We have the execution time for computer B, we have 2.2 seconds. Then we found this much of million instructions per second. Now we found that A is the one which has higher million instruction rate. Now the second question is, which computer is faster? Now if you try to see for the CPU time, we have 2.5 seconds for computer A and 2.2 seconds for computer B. Even though our computer A has higher million instruction rate, it doesn't mean that it's the one which is faster. You see that our computer B can execute execute the same task, the same program in 2.2 seconds, whereas the computer A can perform the same task, the same program in 2.5 seconds, which means our computer B is faster than computer A. The CPU time, we have also to know what is the CPU time. This is given by this expression. The CPU time equals the CPU clock cycle times the CPU clock cycle time. Now we have also this expression which can be expressed as follows. The CPU clock cycle divided by the CPU clock length, which means the CPU time can be decreased by increasing the clock length, by increasing the clock length, or by decreasing the CPU clock cycle. You can decrease the CPU clock cycle or increase the clock cycle. So which means we have the CPU time equals to CPU clock cycle divided by the CPU clock length. So if you wanna decrease the CPU time, you can increase the clock length or decrease the CPU clock cycle. Because we always look to get the result from our computer in less time. Now, the CPU time, we have got this example, and if you still remember, we went through this during our class time. I highly recommend you to go through this if you still have some issues. So, we need first to calculate the clock length for computer B, then calculate the clock cycle for computer A. We have got the expression from the CPU time. Then we can find easily the clock length for the computer B because it is given by this factor 1.2. Here we have another example for CPI. Where we have computer A and computer B, and the cycle time as well as CPI, cycle per instruction. Now they have the same instruction set architecture, which can calculate easily computer instruction. We have the CPU time for computer A, the CPU time for computer B. Then we can find out which one is faster. Since they have the same instruction architecture. Question? Now, CPI, we have different instructions classes which can take time number of cycles. So the clock cycle is given by this expression. The clock cycle is given by the summation from I equals to 1 to n. The CPI, because each instruction has its own CPI, and the instruction counter for each instruction. Get the clock cycle, the CPU clock. So the weighted average for the CPI is given by this expression, the clock cycle divided by the instruction counter, and it is given by this summation, CPI times instruction counter I divided by the If you still remember, we have done this during the class. We have the instruction counter types. We have load, store, arithmetic logic unit, branch, and others. We have the number of cycles for each instruction. We have the percentage of the instruction counter for each instruction type. So we can get this average. We have these CPI formula, so we can apply it here and get the last answer for this type of question. Also, very important to note that AMDA is low. Make sure also you do revise about the AMDA is low. Does help to understand the maximum improvement in performance only when a part of a program is improved. Now, you have the speed up of execution time divided by execution time of the new system after it has been improved. So it can also be expressed by this expression, 1 divided by 1 minus the fraction enhanced, which is the portion of the program that can benefit from the enhancement. That means we have, for example, a portion of the program which can run in parallel. Then we have plus fraction enhanced divided by the speed enhanced. The factor by which there is enhancement portion does not pass. So AMDA is low, it also needs to be revised. We have AMDA is low for multiprocessors. We suppose that we have a pickup system which is used during execution of fraction of time f. Now the speed up is given by this expression. The speed up is, now I want everybody to pay attention to this. The speed up is given by 1 divided by 1 minus f plus 1 divided by SU. This is the most important expression for AMDA is low that you need to understand. And we have done some in-class quizzes related to this. Hopefully that everybody understands this. Now you need to review the number system. Number system. Here you have some problems with number system. And there are some questions related to number system. For example, using 8-bit representation to its complement, you can try to solve the problem. You can also try to do the multiplication in any base. Number system. Please make sure you do revise number system, arithmetic operations, base conversion, sign number representation, logic arithmetic complement. For example, I can give you the number. Then I ask you to calculate A minus B using 8-bit 2 is complement. Okay? Quite easy. You don't do 62 minus 32 is 30. This is for primary school. Make sure you do revise number system. It is very important. As you have seen, we also needed them during the lab experiment. Also, review about instruction sets. I don't ask you to memorize them, but make sure you do understand them. Also, I recommend you to review the microprocessor architecture, bus interface units, which fetch the instruction from the memory, execution unit, addressing mode as well. Now we have a processor structure and the function. We talked about this picture. We have arithmetic and the logic unit. We have status frags. We have shifter, which can help us to do some rotate operation or shift operation. We have complementer, which can help us to do the addition instead of subtraction using 2's complement. We have also arithmetic and the Boolean logic. Then we have the control unit. We have the registers. We have internal CPU registers. Internal CPU registers. We have also internal CPU bus. Now we have control and the status registers. If you still remember, we learned about 8086 microprocessor. We learned about general purpose registers. We learned about special registers. We learned about control and status registers. This is very important. You need to know these all different control and status registers. We have the program counter, PC. We have the PC, holds address of next instruction to be fetched from the memory. Then we have instruction register IR, which is used to hold the instruction fetched. Now, this PC fetch instruction from the memory, then this hold the first instruction. Fetched instruction. Here we have memory address register. MAR. This holds address for memory location. Then we have memory buffer register, MBR, which is there to contain words or data to be written into the memory. Acts as a buffer between the memory and the CPU. Now, we discuss about register organization. We mainly discuss about 8086 microprocessor. We have this general purpose register. We have pointers and the index. We have segment, and we have program starters. You need to understand how many bits is address bus for our 8086 microprocessor. You also need to understand how many bits, what is the length of each segment in our 8086 microprocessor. We talked about it when we learned about the 8086 microprocessor architecture, execution unit, and BIU. This is a register organization from MC16800, and this is for Pentium 4, 380. Now, instruction cycle. We have two steps. For instruction cycle, we have two important steps. The fetch leads the next instruction from the memory, then execute the off mode. This means to perform the operation. We have the start of the instruction, how to fetch the instruction from the memory, then execute off mode. Decode the instruction, execute the instruction. class, please try to review this. Now, instruction cycle state diagram. Now, it starts from here. It starts from here. You need to pay attention here. It starts from here. Instruction fetch. Here we have instruction fetch. You see, instruction fetch, then instruction operation decoding. So once the instruction is fetched, there is the next step is instruction operation decoding. Once the instruction is fetched from the memory, there is a need for the microprocessor to decode the instruction fetched from the memory. Okay? What does this mean? Because if we have here add content from register 1 to the content in register 2, the microprocessor needs to know what is this opcode mean. Okay? What does this mean to the microprocessor? It means to do the addition. That means it means to do instruction decoding to understanding of code. The next is operand address calculation. Address calculation. That means that we have these two operands. Microprocessor needs to know where and where store. Okay? Operand address calculation. Needed to know the address of these operands, especially when they are stored in the memory. Then the next data operation. The next is data operation. Now we got the address of this operand. We need to execute this instruction on this data. Now we got this address of these two operands. We need to find the data and do the instruction. The instruction needs to operate on this data. This data that is given by these two operand addresses. Now here for operand address calculation, there might be more than two operands, more than one. When there are many operands, there are many operand fetch. That means here, the memory will go and decode these two instructions, and here we need to find the operand address calculation for these are. Where is it? Operand fetch for R1, then comes again to do operand fetch for R2. We have multiple operands. Clear? Now we have instruction fetch. We need to fetch instruction from the memory. Once the instruction is fetched, microprocessor needs to do decoding to understand what does this opcode mean. Then that is not enough. It also needs to have operand address calculation. Where are these operands situated? If there are many operands, it has operand fetch to do the operand fetch many times. All right. Now, after this operand fetch is done, we needed to do data operation. So that's where we do addition. combination of the processes of this register number 2 to the register number 1. Then we need them to solve the operand. We needed to solve the result. If we have multiple address calculations of the operand, we needed to have many results. So make sure you also do understand this diagram. It is very important for instruction cycle. You needed to understand what it does, the microprocessor does at each stage of the instruction stage diagram. So this is your 5-minute break. Take your break.